experiment. Okay, so, huh? He's not here today? But yeah, because I mean, I can't remember. There's somebody who's at a soccer meet, I think, in this class. I think there were 2 or 3 people who contacted me and told me reasons why I didn't focus on it because it was at the last minute. But right, that's why maybe it's I'll record this, and if they really anyway, I'll work it out with them. Okay, so the first thing, I was actually looking at this truss that we've talked about before. This is actually really a great example of kind of the summary of what I've been saying all semester. We can see it's a complicated assembly, right? It's like it's a curved. It's not just a simple planar truss, but it is divided into like these modules. And so if you look at this box right here, it's very clearly the truss it's a simple planar truss from a theoretical standpoint, and we could make some attempt at actually trying to figure out when this would fail. But it's also cool because it's got other things going on that sort of make the points that. Oh, and by the way, I opened this up today. They've completely changed the interface for this app. So let me see if I can figure out. I was going to bring in that picture. Yeah, that's not too bad. I don't know why. I thought it was fine before. I don't know why they wanted to change it, but that's the world we live in now. Everything's got to be changed all the time. So here's that truss, and I'm just gonna kind of jam on this stuff. Maybe I'll even go a little bit into areas that aren't as relevant. But because the first thing I noticed about this is it really is, this is a module. So we've got this whole thing. It's part of this larger bridge assembly, but it's clearly this is the truss that we're talking about, and it's separated out from other versions of the truss. It's sitting on 2 connecting points. And so I've said all semester, so what trusses are about is spanning space, and that there's this sort of lineage, there's a lineage that was not mathematical. Well, we built things like this for a long time, and we used our common sense. And if you start looking at, if you do these more and more, you'll start seeing patterns. Like, for example, I see in here, and this is sort of dangerous to bring up because I don't want you in your reports talking about shape just as shape. Like, you can't say, wow, it's an arc shape, which is stronger. But it's true that I see in here, so if we imagine, so these 2 points are being supported. This is an individual unit. So it's like it's a beam, basically. And this out here is the furthest away from the supports. You can kind of see how that's probably in tension. And here's another arc shape that I think is in tension. And then those are going to be countermanded because we're in statics. So this is what I'm talking about, stream of consciousness. I'm going to go, oh yeah, statics. I should mention that, right? So what's statics? Yeah. Okay, great. And they shouldn't move because for every action that we're going to apply to them, there's going to be an equal and opposite reaction, something we know from basic physics. And it won't move, or it will move in a way that we can understand it, or it won't move until it fails, but we'll be able to predict that based on our rules of statics. Okay? So in this static structure, I'm saying that this is essentially a shape. Okay? Now, again, this isn't on the quiz, but I'm trying to point out that there's sort of like that the math and a geometric sort of conceptual way of looking at these things are interrelated. So if I simplify this concept that I'm just positing by looking at it, having some experience, so this is what I think is going on here, this is what I'm saying is happening. And I'm actually going to get rid of these because that's confusing. I'm saying that we've got this and this, and that actually that continues here, and this is here. And it turns out if we put this into the truss analyzer, in other words, if we run the numbers on it, this is what we get, right? So that my concept is borne out in the theory, right? And that's one thing, if you get anything from the classes I teach, it's this sort of thought process, because the theory ought to always make sense. It ought to always be clear that it's also really stupid, like it's, I'll show something about that in a second. So, the theory and the math work out together. But what else do we have just looking at this basic thing? And then I'll get to the really simple one we've always talking about. So we're positing that this is a simple planar truss, but there's so much other stuff going on here. Like, for example, we have these giant joints, and in simple planar truss theory, we've always said that those have no volume. So that's clearly a case where we're talking like what we're doing in the actual truss project, where we have to have a physical joint, and we have to consider how it's going to affect the actual truss. But we also have all this other stuff, like this right here. This is another triangle that's perpendicular to the plane, right? All of these. This is all bracing because it's impossible. Yeah. These here. They are not in the theory at all. All they are is we say we're going to make sure that this truss. Now these are zero force members. The ones coming, or they could be right here. Those are in the plane. But this other stuff, if you think about it, it's outside the plane, so it doesn't exist in the theory. It's part of that box that I drew one time for simple. Maybe I'll do that in a second. So this is just us. So when we say, okay, we're going to make sure that this truss stays is planar, because that's the theory we understand. So in the real world, we're going to have to hold it up with other stuff. And then that other stuff becomes part of our theory. Or we have to theorize on it, and we have to size it and everything. But that's not what we're dealing with in this class. We're just dealing with the truss, right? So I'm just pointing out that it's more complicated, but we're still, obviously, they're using simple planar truss theory. Why would they make this truss look like that, right? It's part of this long history we've got. Okay, so that's basically us looking at this truss in the wild. But what I've always been doing is focusing on a single triangle, right? So let's do that and then keep going with our little theory review. So here's the idea. We have a triangle, and we're saying it's part of this lineage up here of theorizing mathematically how this thing is going to perform when we actually build it. So how do we do that? How can we possibly go from a triangle to saying, I'm going to build this over there across from Whole Foods and not kill a bunch of people? So we came up with this thing called simple planar truss theory. And the first thing, the planar part of it, let's imagine this is the universe, this box here. And there's a plane that we are going to constrain our truss to. Maybe I'll give it a color. So that's the planar part of simple planar truss theory. Why do we do that? Why do we say it needs to be in a plane? Because if we can tell ourselves that we're going to constrain our geometry to a plane in the real world, then when we load this, there's nowhere for that load to go except through the centroid of the member, because the member is only a centroid. It's 1 point thick, right? It's in a plane. That makes statics so much simpler if we can just say we're not dealing with all this bracing. We're just saying what happens in a plane. Then we can go a long way. So the next thing we have to do, though, before we even talk about that, we're saying, okay, this is going to be in a plane, and we're going to load it. We've got to have it sitting on something, right? So we somehow magically constrained it to this plane here, but it has to be some distance from, it has to be sitting somewhere. It can't be moving because, we're constraining it to plane, so now it's static in that plane, but, it can move around inside of it, right? So we have to connect it to something, which is the Earth, always. And so, great, that's obvious, and we have to talk about a little bit exactly how we're connecting it. But now we've got it in a plane, constrained to the ground. What else do we need to do? Well, we've also said it has to be, and clearly this is not symmetrical, that drawing, but it has to be symmetrical and made up of triangles. The way to conceive of that, and I'm not sure, again, how, I've written one quiz, and I hope to write like 3 or 4 more so there won't be everybody taking the same one. And probably by me doing these reviews, I might go, oh yeah, I should put that in there. So I don't really have a concept exactly how I'd question you about this, but, and I've got to fix this is driving me crazy. Sorry. But all the theory only makes sense in the context of what I'm saying here. So I think it's worthwhile to bring this up one more time. Let me move my P over. Okay. So why triangles and why symmetrical? Well, first of all, if we think about, so we're spanning space, right? That's the whole point of it. And if you remember like some of my lectures, the whole idea of trusses is that, yeah, so we need to go from point A to point B, spanning across something. Let's use as little material as possible because, you know, why? That's the whole kind of point of engineering is being efficient, right? Or one of the points. So let's figure out a geometry where we can get rid of most of the stuff and just have very little material left. And it turns out that triangles are really good at that. And so we've developed this triangular sort of vernacular for structural designs. So why then would we want it to be symmetrical? You think about it, if you're spanning across something, you're going to have a center axis, right? There's going to be a center to that. And if you make one side, so if I make this side stronger, sorry, that's not very clearly drawn, then this side is going to fail. So what good was it to make that one side stronger if the other side's going to fail, and vice versa, right? They should both be the same, or we're just going to waste material on one side. Now, unless, of course, in the real world, there's going to be reasons why they might not be symmetrical because you got different things going on, but whatever. This is theory that we build from. Like if you're a musician, you know, you learn jazz, really boring, all these rules. You learn it so that you can break the rules once you understand the rules, right? Okay, so that's the simple part, is that it's symmetrical and made of triangles. And the way this could definitely be on the quiz, the way we mathematically express that is the number of members equals 2 times the joints minus 3. Does that equation make sense to anybody, or does that just sound like, I mean, it's just really simple. If we say, I'm going to add a triangle here, and a triangle here because I want to be symmetrical. I've added 1, 2, 3, 4 members and 2 joints. If you plug that into here, that's going to keep us within members equals 2 joints minus 3. That's all that equation is, okay? And I've said before, as you're developing your iterations, what you want to do is just be systematic and just make sure you're adding the symmetrical triangles on each side. Then you'll always get, in the truss analyzer, you'll get the, yes, it's a truss indication. Okay. So now if we've got it simple, planar, the one other thing we need to do though is, well, maybe we can go a step further. Without really thinking about anything else, we can commonsensically imagine, so here's my load. It's obviously, it's going to the support point, so it's coming down through here, right? If we're talking about statics, then, actually that's an unfortunate color to use. Let me go back. I meant to pick this one, I think. So this is coming down here and down here. We know, just using sort of common sense, that, well, then that means that if this is statics, this member's got to push back. So it's going to be in compression, going both ways. It's pushing against that force. And so that means this is going to try to push out this way. We've got pressure on this joint. But the reason that we choose triangles is because now this member is going to pull back on that. And so it's self-supporting. That's kind of the whole idea. And the way we've been summarizing that then all semester is that if we, whoa, there it is. That we can commonsensically say this is in compression, this is in tension. They are equal and opposite to each other, or they're not equal because we're going to do the trigs. They're not equal, but they are in opposition to one another. And so in simple planar truss theory, we say these are two force members, because since it's just a plane and there's only one point of material could go through, it's going to have to either go this way or this way. It's going to have to be either in compression or tension. So what's compression and what's tension? Anybody? Yeah. Okay, you're getting further into our theory. Compression is just, yeah. Compression, squishing, tension, pulling. That might be something done in a more, engineeringly correct or exact way, but that might be on the quiz, complete giveaway. But yeah, so we've got, and then we're going to get to buckling in a second or in a couple minutes. So that's the only two options. So basically, by creating this conceptual universe within which this triangle exists, we have now determined that the members can only be in compression or tension. We've set it up to where we know that and we can even conceptually imagine which ones are in compression or tension. We understand that this is going to be. We typically think of it's just a convention, but one is going to have to be minus. And one's going to have to be plus, so they're opposite to each other conceptually. So we're that far. That's great. But we got a couple other things we have to do. Oh, and then we had I'll go and include that. So we just have, and the number of members equals 2 times the joints minus 3. Okay, so what else do we have to do? Well, we have to consider joints, and we have to actually be able to get numbers now. Right, and that's kind of the cool jump, is how do we get from this conceptual world, which we can use to build things. We don't need numbers for it. We could basically do a lot with this, but we say, okay, we want actual numbers, and since these are triangles, and we know a lot about triangles through the history of humans and math, and we know Newton did the force parallelogram, and we think, well, yeah, we can conceive of these as actual like XY coordinate force, relative force magnitudes, then we can, if we can get a certain mathematical setup, then we can actually get relative numbers out of this. And the way we do that is that we say, okay, we know this is statics, and so that the sum of forces about x, because if this is obviously x, this is y. Sum of forces around about x equals 0. Sum of forces around y equals 0. And we have this thing of that you've learned in statics, that we can say that the sum of moments around any point need to equal to 0. Bound, I'll just say z equals 0. And so we have 3 unknowns, and if we set this up to where we have 3 forces, Fy, Fx, and Fy, or I'm sorry, this is a Fa, Ax, Ay, By. Now we have 3 reactions and 3 unknowns, and we can do our trig and get actual numbers out of this. If we know the lengths of, I've always been using 15 and 4 because that's how big our truss buster was. Now we can get to the math, right? So what might then be asked on a quiz from any of this stuff? What's a load? It's a force interacting with something physical is what I would say. So, because in our case, and again in physics, these would often be called forces, but to me they're loads, because a force is a vector in space. A load is when the force contacts something. You might need to know what the what is simple about a simple planar truss? It's triangles, and number of members equals 2 times joints minus 3. Some description of why it's called a planar truss, what a two-force member is, some description of statics in terms of, hold on a second, in terms of that we have to have the number of reactions and the number of unknowns have to be equal to one another. Yeah. What makes it simple is that it's triangles that are symmetrical about a central axis. And again, this is Professor Snell world. I mean, you can go look it up elsewhere. Go look up, what was I looking at the other day? Look up luminosity. Because like in D1 right now, we're doing, we have the photocell. If you look up just in Wikipedia, luminosity, it's like really crazily complicated, and it's correct because they're talking about it from a technical standpoint, but all luminosity is how much it is the amount of light hitting a surface, really. So anyway, I kind of maybe am simplifying this in some degree. Okay, so now the last thing we have to do is talk about the joints. And then I'll get into the beefier stuff, probably that's mostly going to be on the quiz. Because in simple planar truss theory, the joints are infinitely small and therefore infinitely strong. So we know when we're going from the theoretical world to the physical world, we're going to have some way to theorize or to design joints that will meet this theory, which means they have to be infinitely strong in whatever universe that we're building them, right? So another question might be something like, what is the strength of joints in simple planar truss theory? Or how big are they or something like that, just so you get the idea that they are there only because they have to be, because you have two members coming together, but they're not theorized in any way. So they're infinitely strong. Yeah, and infinitely small. Yeah. Exactly. They exist because we have a real world and we know they're going to have to exist. But then in the theory, there's another thing that I really, that I've talked about, but maybe you guys haven't gotten. So I'm going to spend time on that right now. And I promise this will end at some point. But I don't know, to me, this is all interesting, and it's what we've done in the class. Why do we call these joints hinged? Anybody remember? Yeah. They don't resist moment. Right. Okay. Perfect. What would it mean if they were so what named joint that we have talked about resists moment? Do you remember? Gusset. Well, okay. They're actually in that's funny because like if you go look at Professor Shapenko's example, he's got gusset plates all over the place that are they're riveted. So you could say they're pinned, but you could even weld those and they might not be fixed because it has to do with where they are in terms of the joint. We haven't gotten into that. So a gusset plate could be fixed or hinged, but what I was asking for is fixed. And so let's just go over that quickly because this is getting into buckling. So this is sort of preemptive, but it's important to the why these are always hinged. Here's that typical drawing you see. We say that so this is a beam up here or whatever. This is a slab. What the hell with that? And these are columns. So we can have hinged, fixed, or I guess we can have hinged, fixed. What happens, and we have these different KT values for these, right? Actually, I'll put that over here. What's the KT? This would be something that might be on there. What's the KT for a hinged? 1. Fixed? 0.5. And process of for a hinge fixed? Yeah, 0.67, let's say. Whatevs. Why is this? This is not like this is not calculus that was used to generate this number. It comes from this conceptually, at least in the way I understand it. In a hinged, column, you have the entire length of the column, LU, is available for buckling, right? So 1 makes sense, the entire length. In a fixed that is not that is resisting moment, we have this, something like this, and here we have this. So what we're saying here, if we zoom in on this joint, we say that as this is loaded, and this, so this is trying to go down, this 90-degree angle is not going to give, right? It's going to resist that moment, and it's not going to, because moment is twisting, it's not going to twist, and so therefore it's going to stay straight for a while. And so what this actually does is it reduces the length of the column that's going to be buckling. So since we have no joints in a theoretical simple planar truss, I think that's where it comes from, really, is that, well, first of all, there's 2 ways to go at it. It's the full length that we're dealing with. The way we're going to get a full length in theory is using hinged. Also, if we set these up to where they're resisting moment, that's called a moment frame. It's just a different theory, right? Because we're going to have different lengths that are actually available for buckling. So now we kind of jumped into buckling for a second, because now, so what's LU? Unsupported length. And that means it's the length that's available for whatever force you're talking about. So in this case, it's buckling. What is the effective length? Right. And so why would that be? Effective length means what? Yeah. So it's the length. So effective length is the actual, and again, this is conceptual, the actual length of the member that's available for buckling. So it's the in condition factor, that's another term you might hear on the quiz, KT, times the unsupported length is the effective length. Does that make sense? So what's the cut length? Cut length. It's the full length. It's the thing. It's what you buy. So it's what they're cutting at the factory, right? Okay. So now we've covered the geometry. And the thing I really didn't say at the very beginning of all this, which is like, I've got to think of a question of how to say this, because the whole point of this is that we've got a thing that we're calling a truss, a simple planar truss, and we're trying to theorize how it's going to respond to forces, to loading, and at what point it's going to fail. The way we do that is a combination of geometry and materials. Okay? So right now, so far, all we've been talking about is geometry, right? But at this point, if we had these numbers 15 and 4, and we could actually get numbers for these, and we've done this a bunch of times, right? This is 100. If this is loaded with 100 pounds LBFs, this is going to be 106.4 LBF, and this is going to be 93 or 4, something like that LBF, right? So we can actually get loads if we know the load on. We can get loads in the members if we know the load on the truss, right? Now, the reason I always draw this single triangle is it's very simple to do with one load. If you're actually, and so we could actually very quickly do this by hand. But if we have a bunch of triangles, you want something like the truss analyzer, because we've got a bunch of loads. It can get very time consuming to do the calculations. And do you also understand, it's really important that in the truss analyzer, we don't want maybe in Shepanko's version, but what we're really talking about is the relative loads in the members here. We're not, because there are no actual numbers. We're not getting failure loads out of this because we don't know what the thing's made out of. And that's the next thing we haven't talked about at all, right? So this is all geometry. But how do we get, and we can get relative load ratios for different members for as complex a simple planar truss as we want to draw. But that doesn't tell us anything, because if it was made out of marshmallows or if it was made out of steel, it's going to have a completely different performance, spectrum, right? And if anybody wants to, you can open these windows because it is hot in here. Remember this? So it was really cold last week, right? Yeah. So we put in a work order, and they're like, okay, you're cold, huh? Well, just like make it. I could almost predict it. And we were joking because in the D1 lab in the basement, it was really hot last week. At the same time, it was cold up here. So it's an old building, but I don't know. I think that we need some mechanical engineering consultancy here. Okay, I'm gonna take my hat off, definitely. So we've got the geometry rocking, but now we've said that we know that these are two force members, either compression or tension. So we got to learn about compression or tension, and we have to learn about how these joints are failing, and that ends up being shear, right? So let's go over those. I'll try to do it more quickly, but is this helpful? What I'm doing? Okay. So let's go systematically through tension, compression, shear. So we drew this a bunch of times. We said, okay, let's start with tension. If we are, and let's imagine, here's a specimen. It's connected to something down here, and we're pulling on it. So remember, there's always going to be a response because this is statics. If we draw this axonometrically, looks like this. And we're saying we're pulling, and again, simple planar truss theory, we have to be pulling through the centroid of this member. That's all that exists in the simple planar truss. So if we're allowed that simplification of the world, then we can say, oh, okay, we've got a theory for this. Now, again, we didn't just make this up in this class. This is developed over a long period of time. There was a lot of experimentation that went into it, but now we have a simple conceptual theory that we can teach ourselves, which is if we're loading something through the centroid, so it's a normal load. That would definitely be something that might be on the quiz. Perpendicular, normal load. Then we can, and it's in tension through the centroid, which is what the normal load would mean. Then we can conceive that the load is being taken by the cross section, and actually by every cross section of this specimen. So that means then that this is the cross section. We have X and Y, that the load is dispersed through this material. And we have and we're calling this stress. It's the internal response inside a material. And I guess the internet's really slow. That's why in this class it usually is. Because there's a lag on makes it hard to draw. So stress and tension is the internal response to loading. Okay, that's something that could be on the quiz. And the formula for it is stress equals load over cross-sectional area. A equals XY. And all semester I've been calling just A is cross-sectional area. And so if it's parallel, I've been going A parallel next to it. Okay, great. So that's good to know. Then we've said if we look at this in elevation, so that's the internal response. If the external response is going to be, it's going to stretch out. Right? And that's going to be a change in length. It's also going to get, oh, come on, man. It's also going to get a little bit thinner. Give me a break. So it's going to be a little bit thinner from the original. It's not a very good depiction of it because as you stretch it up, it's a volume. Man, I'm sorry. I have no idea why this is going on. Now it knocked me off of there. Seems to have to do when I set it down, so maybe it's just the drawing of it. Okay, And so then this is called strain. And it's the external response, right? And is stress and strain, are these properties of geometry or of material? Right. Very important distinction. I don't know why this is losing its mind here. Let me see if I do that. Yeah, okay. And its equation is strain equals change in length, or displacement is another term we use for it, over the working length. Now, why would it be called a working length? Because that might be another term on the quiz. Remember our specimens? They look something like this. They had threads. Okay, let's dive into this for a second. If this is a specimen in tension, why are the threads wider than the part we're measuring? Yeah. Right. And why would wider make them not fail? Just call out. The area. This is what it is. It's just that the area, if the load is the same and the area is larger, it's going to be stronger because there's going to be less stress on it. Stress and strength are the same term. When something is as strong as it something's strength is how much stress it can take. So, okay, so we make it wider. So these are infinitely strong, just like our joints. Again, that's kind of the, we can say infinitely strong because they're never going to break in the universe of this sample. Then there's a fillet here. Now there's functional reasons for that fillet, structural reasons, but it's also because we're bringing it down to a known diameter at an exact point, because we want to know exactly this length, which is the working length, because that's the amount of this specimen that's going to be under tension, right? So then we go and the whole kind of way that we interacted with this information was we did a stress-strain diagram. And from that, there's tons of questions from a potential quiz. So we've got stress over strain. This is always, in our class, has been in PSI. This is unitless. We usually say it in percentage. Okay, so let's talk about all the things that we learn. And again, material, right? So if we start with geometry and we apply material theory and again, this is all theory. We don't need anything. We could do this on a desert island if we had a computer, I guess, or I don't know. We were good with coconuts and sticks. We can learn a lot about the material through a stress-strain diagram. So, questions. What is the slope of that portion of the curve right here? What's that called? Yeah. Modulus elasticity, or Young's modulus. I won't ask this, but why do we limit? This kind of might be, this may bring a question that's possible. We measure it between a very specific set of strain values. It's actually strain values. It's like 0.0005 and 0.025 strain, which is actually 0.05%. Why would we do that? So we're saying, the Young's modulus, or modulus elasticity, is the slope of that line. So it's stress over strain. Why would we only measure it at the very beginning? Yeah. That's true. That's definitely true, but that's kind of more up here, right? Why would we, what I'm trying to get at, and this is a fine point, and nobody got this right on their individual assignments. So we would measure this at this point because the further we stretch it, even though this is supposed to be a straight line, the second we start stretching it out, it's going to get thinner, right? It's going to have a less area, and then therefore that's not going to be a straight line anymore. It's going to slowly start getting steeper because there's going to be more strain because it has less area. So if you look it up, and I probably won't add this because we didn't really talk about it. I think I mentioned it, but that's why you have what's called a working stress and an engineering stress, because the working stress would be taking into consideration this infinitesimal, constantly changing stress over strain. Engineering is our conceptual stress, right? But the point is, maybe if I plug this back in, I just have trouble drawing it when I'm, maybe that's because that's upside down. That's what it was. I was pushing buttons. That was upside down. But the point is that, yeah.
So it's the stress is based on the area, and then since the area is changing, we can't change the area as it changes.
Right, exactly. Now we could with a more complex computer program, but also we're always we're like, okay, let's back off a little bit. Let's just kind of simplify this. Let's just measure it at the very beginning. And also it has to be a standard. I got you. Whoa. Got to turn my phone over. I'll call you in just a second when I finish this thought. We also need a standard. We need to say, this is gonna be brass 260. There's a certain way you're gonna have to manufacture that. And when you test it, and you tell us what the Young's modulus is, you measure that between 0.0005 and 0.025 strain, and everybody does that. Then we're comparing apples to apples. Yeah.
Is it also, I think, it's very cool because that's like when it's like the most ideal. It's like right before it really starts.
Yeah, right. It's exactly. He's saying, this is when we haven't done anything to the material yet. It's in its kind of purest form. And the best way to understand that is that we get to a point where we really change the material, right? But it's already changing through this whole thing. But the cool thing about this, which again, this stuff blows me away. This is one of my, and I'm sorry if I'm kind of bombastic about this, but this is not what I do in my. I do carbon reduction in building envelopes. I can go an entire semester in my job and not use the word building even. Right? So this is not my area at all. And I still am always blown away when I'm teaching this. I'm like, man, the stuff we figure out, it's incredible. So you should have, hopefully that you can bring that kind of interest to these things because they are incredible. Yeah. So it's 0.0005 to 0.0. Oh, on the 2.5? Yeah. You're right. Thank you. Right, because it's 0.025%. Actually, I think it's from 0.05 to 0.25% strain. Thank you. Okay. And so this is a material property, like you were saying, especially when it's in its purest form. Every material that we test that's made out of this and has the same cross-sectional area, et cetera, should have the exact same response, right? Okay, what else we got here? We have this point. I'm going to circle these all in red, I guess. So what's going on right here? Changing from the elastic to plastic region, and what does that mean? What happens what happens in the plastic region? Yeah, just call it out. Right. And when I first was learning about this, I was like, plastic? Why is that plastic? But that makes sense. I mean, I'm thinking of like a piece of plastic, but it's true. Plastic's rigid. Rubber band isn't. So these are descriptive terms that make sense. And we didn't talk about it, but actually, so then, wherever you determine that region, actually the area underneath here is the amount of work being done in that portion of the curve, but I'm going to actually get rid of that because I'm not really. You do need to understand that the elastic region would be the portion of a stress strain diagram related to because the idea is this. So this continues on. This is the linear. The elastic region is the linear portion of the data curve, and it's linear because it's proportional, right? You add more force, you're gonna get a proportional amount of additional strain, and that's why this is also called the proportional limit. So that's either the yield point or the proportional limit. What is this number though? If I go over here to the y-axis, what is that number? I couldn't. You said something about failure, so it's the yield stress, right? But the reason I'm saying so, the yield point, yield stress. This could be strain at yield. But the reason I'm bringing this up, so in your modelers, when you're talking, so when we get down to the, actually trying to put numbers to our trusses, we're going to have Euler and Johnson's, which are loads, right? We're saying at this length, this member is going to fail at this this load if it's an Euler length. Then we're comparing it though to a pure compression value. That's load at yield. And why yield? Because Johnson decided that, because he put that in the equation. It also makes sense because we're saying in structures, we always want to keep below the yield point when we're designing things, because once we get past this, it may not fail, but it's going to be damaged, and now it's a new thing. It's not static anymore, right? Okay, let's keep going on this. So obviously yield stress, loading, that could be loading. What's the load at the proportional limit? I mean, that's maybe a little bit tricky, but that's load at yield. Okay, so then what else do we have going on here? What's this point? Ultimate tensile strength. That's and what happens between here and here is that I mean, this is somebody could call me on this. This is a simplification, but the way I've read it is basically this is a molecular rearrangement of the actual material in response to the stress. So it's actually you're changing the material at this point. There's other ways you can change it. You can heat it up to anneal it. There's all sorts of things you can do. But so it actually it can take more stress past the proportional limit. But so obviously the slope's going to be much higher, much faster, or lower. And then it gets to a point where that's the most it can take. That's the UTS. I'll just say Y here. Then what's this point? Yeah, and that could be load at fracture. It could be stress at fracture. And so if I said, what is the X value at fracture called? What's that going to be called? So it's going to be the strain at fracture, or percent elongation at fracture is what we're actually calling it. So that's another quiz, very potentially quiz question. Percent, that was in that first percent elongation at fracture. And then the load at fracture would be, or stress at fracture would be the Y value here. Okay. So the point, so those are all things that can be on the quiz. But the point of this then is that, and this is going way longer than I thought, but I think it's useful. So thanks for bearing with me. And again, we won't be doing this anymore. The point of all this is that now we know something in tension about this material that we can have published specs about it, right? We can say if you're telling me that it's brass 260 fabricated to ASTM A36 or whatever, and you've tested it using this ASTM convention for modulus elasticity, then I can just I don't even have to have it. You're going to send it to me, and I can design all my stuff and use that material, and I'm going to be confident it's going to perform the way I expect it to. But what else there's a really important thing that we learn from this about tension generally, which is, does the length of a member in tension matter? Yes?
No, because
Yeah, right,
And like it should like fade out of existence and just like pop. Like,
right. That's
it doesn't.
that's great. I'm glad that you. Yeah. So that's what I like to say about it. So exactly right. What he said is that it's this cross section. If every single one of these cross sections is taking the load, doesn't matter how many. It's all, and they're all taking the same load. It doesn't matter how many cross sections you have. We also know it mathematically because there is no length in this equation, right? So that's how we get suspension bridges, right? Because somebody went, okay, why are we using all this steel and compression and this big heavy stuff? We just make cables. They can take a lot more load, or they can be much thinner and take a similar amount of load. So that's very important. But what he was saying, which I think is really a good thing to remember, and I've got a picture of it that I've shown before, is that if our theory were accurate, this thing, what would happen? I guess it would vaporize, right? Because like he was saying, you'd pull it up and keep getting thinner and thinner, and then since every single cross-section is taking the same load, at one moment it's just going to go pop, and you're not going to see it anymore. And like, oh yeah, that's great, tension. That's not what happens, and you can go look, I don't think there are any here now, you can go look at a pile of these that have been broken, and they're broken all different places, and it's because there's some kind of imperfection. That's at least the way I understand it. And once that imperfection is enough to create a difference in that response to the load, that's going to get exacerbated. A feedback loop's going to happen, and that's where it's going to break. So it's going to break, here or here or here or here, any of these different places. It's not going to vaporize. Okay, so that's tension. What about compression? And so basically what we're saying is we know now, if we're making a modeler, we can get an actual number for whatever member that is. It's not going to have anything to do with the length. If we know what the member is made out of and its cross section, we're going to calculate load at yield, and that's where we're going to assume that member would fail. Okay. And so that would be something on the quiz. It's how do we know, or what formula do we use for a member in tension to figure out when it's going to fail? Clear? Okay. So buckling. The most basic, I think, thing to understand about buckling, because that's, come on, man. Actually, I'm going to switch to this for a second. Remember that this is like the whole class right here. And so you really need to understand everything about this. If you understand everything about that, you'll have a good project. You'll probably do pretty good in the quiz, I would imagine. I mean, I shouldn't say that because there's more stuff. But so what's going on here? We've got right here. This is load at yield. So that is a member in pure compression, right? It's going to be strong because it's just, imagine taking a penny and trying to compress it. It's, and it's analog. It's the same equation as for pure tension. Pure tension can be a long cable. Use the equation. It has to be a really short, fat thing, but that's the same equation. So here's our red dot in this modeler. And then this is Euler's and this is Johnson, which we're getting ready to remind ourselves about. Euler's is a theoretical equation created in, I can't remember what year, a long time ago, hundreds of years ago, where he's relating modulus elasticity, moment of inertia, end condition, and unsupported length with some constants thrown in to get a failure load. So he's relating length to failure load. And but the problem with this equation is that at some point it gets ridiculous. Clearly, we're going to get to infinity, and we know that we can't have an infinitely strong material. So, and we also knew, but we know when we get short and fat, we'll be able to crush it. We don't need to use the length for that. And then so this guy Johnson said we need something, and I think for a while that's all we had was Euler's. There hadn't been a theoretical calculation made to get us from Euler's to pure compression, but that's the whole point of Johnson's. All it's doing is pointing at load at yield. So if I want to demonstrate that, I'm going to change my yield strength here. If I can get my mouse, okay. Yeah, see, all that happened was I changed the load of yield, and then Johnson just pointed at it like a pointer dog. That's all that equation is, and it's as far as I understand, it's empirically derived, right? So it was just done through experimentation, and what he did was he said, okay, Eulers, what's wrong with Eulers? It's not dealing with yield. There's at some point yield comes into it. When does it, and how does it, and that's what the parabola is. And if you look at the equation, that's what's in there. Okay, so if we go back to the drawing, what I'm saying there basically is if we have a short, fat thing, it's going to respond just as we did in, sorry about that, it's the stress, I'm going to say in compression, is load over cross-sectional area, and the same idea that these cross-sections are taking the load. Then we said, okay, but then if it's long and thin instead, obviously it's not going to compress. It's going to buckle. And we had a whole thing. I had that SketchUp model showing basically, conceptually how this works. But the question is, how mathematically is that different from stress? And we came up with, or not we, but Euler came up with what I've been saying is EPCR, Euler critical buckling load, pi E I. Sorry, this is just so laggy right now. I'd love to know what's going on at this time, because this isn't true in other sections for this class. And then I'll just go through it quickly, but if anybody has any questions, make sure you let me know. But the most important thing is we're understanding that we're outputting a load here, not a stress, but we do have stress involved. So it's they're intimately related to each other, obviously. So where are we getting E from? Yeah.
Material.
Right. And it's so we have to know the material for this equation to work. It's the modulus elasticity. It's the strength of the material. It's also called the stiffness. That might be on there. Why stiffness? Because it's staying stiff until it starts to be molded after the proportional limit. Okay. We know pi, obviously. KT in conditions. We already got that. LU we've already covered. I, we haven't. So what's I? Moment of inertia. And can somebody describe what that is? Yeah.
How far the area is out from the center?
How far? Well, not the area. But that's good. You're summarizing it the way I was trying to summarize it for you guys to make it simple. What you're saying is, so moment of inertia is the resistance to buckling about an axis. Okay. So let's just stick with that. Resistance to buckling about an axis, moment of inertia. Is it a material property or is it? Yeah. Geometry, right. Now, it's geometry in the context of material, so we can't use it without the E. But right, it's geometry based. But now we're not talking about truss geometry, we're talking about cross-sectional geometry. And that's the whole, like when you get into radius of gyration, the square root of I over A, it's like how efficiently you're using the area, right? So it is shape, not just area. It's not the pure amount of stuff, it's how it's configured. But the simple way we've been conceiving of it is what you're saying is that the more stuff you get away from the centroid, the stronger it is about a given axis, right? And so that's why, so here'd be a question. Why do columns tend to be symmetrical? Yeah. Right. So we're saying that if you have these two columns in cross section, this one is going to have the same moment of inertia at both these axes, whereas this one's going to have a big moment of inertia around this one and a small one around this one. And so it's going to fail based on the small one. You're going to waste a bunch of materials because this column is basically this column. All that material outside of that is wasted. You guys get that basic idea with moment inertia? You could answer a question about it, however it's worded. Okay, and so then other things that you're gonna, that you just might come up with questions is just simply saying things like if the end condition is larger, what is the load higher, the failure load higher or lower? Just understanding where length has a huge effect. Squared is it longer or shorter? Make things stronger or weaker? Yeah. No, you want to remember the equation. You'll be given the equation. But good point. I might, I'm assuming that these equations will be on the quiz, just because that's the way it's going to shake out. But without an equation, I could say, if you're in an Euler, well, if a column is going to buckle, is it stronger if it's longer? If the LU is greater, is it stronger or weaker? That's fair game without looking at the equation, right? Okay. And then we already said, so this was, short, fat. This is long, slender. And then we had something in the middle. And the whole idea was that's got a different equation to it. Let's see if I can remember it. Johnson's equals, what is it? Yield minus 1 over E. I just can't keep, there's such a lag on this, I can't even, times y over 2 pi squared times slenderness ratio times area, whatever, squared. Nothing's even happening. I may have to quit this. Yeah, there it slow. Came up after I walked away. But if you look at this, the only thing that's changing is the length in both of these equations. And so then we're back at this. Euler, Johnson, pure compression, right? You should understand that chart, how it works together. Let me think what else quickly with this. And this is some data here, and understanding the idea that if we're measuring data, that we can derive an equation from the trend line that's doing the exact same thing. So if we test something in buckling and do a bunch of specimens like we did, we can actually get an equation that does the exact same thing as the theory. Yeah.
Johnson is used for columns that are short, not short.
It's just that it's between the two, and that's okay. And the other thing to think about, it's really what in the real world what it comes down to is slenderness ratio, which is that's in the equation. And slenderness ratio is the effective length, KT times LU, over the radius of gyration, which is the square root of I over A. So you basically say, so the bottom of the slenderness ratio equation is how effectively you're using the area to resist buckling. Because square root of I over A, if you just think it through. And the top is the length of the member that's exposed to buckling. That's the slenderness ratio. And so that's really what you're considering in the Johnson's equation. But the point, and that's why it's good to bring this up, though. What is this line right here? Critical length. And what does that mean? Transition between what and what? Okay. And so it's the length. So anything larger than the critical length is an Euler length. Anything shorter is a Johnson length. And how do you get the critical length? Critical slenderness ratio. So think about it. So that the slenderness ratio is, the critical slenderness ratio is a slenderness ratio. So if we say slenderness ratio equals critical slenderness ratio, in the critical slenderness ratio, in the slenderness ratio, there's a length, KT, LU. In the critical one, there isn't. It's another equation that has to do with Euler's, with E and Y. So then you can solve for L. And so then you can say the critical length, you can solve slenderness ratio equals critical slenderness ratio, solve for LU, which is going to be the critical length, okay? So some people are doing this by solving for the slenderness ratio, that's fine. But that's really important to understand that that's all you're doing in the truss analyzer, or in your truss modeler is saying, we go back, so okay, I think that, let me look at my notes. See if there's any terms, load ratio. Okay, let's, I'm sorry this is a little bombastic, but this is just stream of consciousness. What are the, I'm going to call these load ratios, and do people understand why? Yeah?
Not actually load, it's the ratio to any theoretical load that's placed on it.
Yeah, it's the percentage of the load in the truss that a given member will take. And so it's relative between the different members. Yield, elastic plastic. We didn't talk about shear. Let's just do that super quickly, because this has gone on too long, but I don't really know how to do it shorter. I do have this, I can kind of move through. Let me just get to one of the only thing that's different about shear is that we're positing that, come on, that we're saying we have a hinge connection, so we have a pin or a number of pins. They are taking the load through the cross-section like we're saying, but that cross-section is actually parallel to the material instead of perpendicular. So it's the same cross-section, but it's taking the load differently because it's a sliding force now. So it's completely different. In other words, we're using the same equation, but we're going to get a completely different result with the same material. Interesting, right? It's because of the orientation of the force or the load to that material. Does that make sense? And when we're calculating this, we need to consider how much, what part of the pin is taking the load. In this case, it's what we call double shear, because I'm trying to get to that. Oh man, this is so slow. There's 2 points, 2 cross section that the load is taking here and here. And the idea is that then that is then transferred. So the load goes to the pin first and then is transferred through the centroid. That's another basic thing I didn't say about simple planar truss theory. The loads are only, they're considered to only arrive at the joints, okay? And I think the way to think about this is, like, let's say you have a big truck, you have a bridge or a house. The bird lands right here, you're not worried about it, right? You're worried about the internal, the loads that are being distributed throughout the entire assembly. Let me see if there's anything else. Slenderness ratio, I mentioned that. Profile, make sure that cross-section is profile. Cut length, buckling, hinge. Okay, a couple. Brittle, I said, so did I say this yet? So, okay. Maybe I didn't mention this enough to put on a quiz, I don't know, but it's pretty simple. So a material that is has a stress strain diagram like this one. Oh my God, it's so hard to draw on this. That would be brittle because it's very strong. Actually, I should have made that steeper. It's basically very strong, but it has no elastic region. No plastic region, so it breaks it fails very quickly. Ductile would be more this one, where it's has a large plastic region. So like in structures, you can call assemblies brittle or ductile too. In earthquake regions, you make ductile assemblies so that they can move around. And maybe they're damaged, but they won't fail catastrophically really quickly. Load at yield, I mentioned, percent elongation of fracture, Johnson's parabola, Euler's critical buckling load. Shear stress, parallel load, right? Tensile stress is a normal load, ultimate tensile strength. Those are all things in my notes. So let's to wrap up, what was I thinking in terms of looking back at this? Right. The whole point of all this is that now we can take these ratios and now we're talking project. Somebody tell me, and I did this last week, right? We talked about how to get what the failing members are and what the truss failure load is. Okay, so how do I figure out what the failing members of a truss are? Yeah. Okay, except that what if it's the highest load ratio if they're all the same length? So it's a relationship between load ratio and actually failure load. Okay, so we're gonna, when we get to from this point, we're taking this information, which is all just calculations, it's just geometry. We're going out from geometry into the world of materials, tension, compression, which is buckling, and shear. Actually, only compression and tension for the members. And we're calculating, because we know the lengths of these already, we're calculating failure loads with our tension, buckling, and buckling equations, right? So that means you have to have 3 equations you're comparing for every single member. You first have to say, okay, is this member in tension or compression? It's in tension, I'm going to use the load at yield, right? If it's in compression, then we have to figure out if it's an Euler or a Johnson length, and then use the appropriate equation. The point is, you're going to get then from that a load, right? So from this data, we will be able to know the loads on every single member. That's the first thing. Is that clear how you're doing that? So when you turn in your modelers, because I haven't seen any modelers yet that have all this in there. So just make, that's what you're going for, unless you're doing the Shupenko thing, and that's a whole different approach maybe. And that's not I haven't really focused on it, so you're gonna have to really explain to me what you're doing there in order for me to help you. Okay, then we know what each of those members would fail at, but we don't know if they're gonna fail because we don't know when they're gonna get to that load, right? So it's the members that get to their failure load fastest or first that will fail. So that's where the load ratio comes in. So it's either the load divided by the load ratio or times the load ratio. You got to play around with it and figure out what it is. But you'll get, or because you could do it either way, because then you could say then it's going to be the highest negative number or the lowest negative number, or however you want to conceptualize it. But that will relate them to each other, and you'll be able to get relative numbers. Those are not going to be actual numbers you use. They're going to be how you figure out which are the failing members. And then you're going to be able to say, okay, these 2 members are failing. And let's say that, again, these should be really ratios at this point. I don't want it to be 100 pounds. I'm going to say it's 1 pound, so it's really clear. So 1.06. So let's say the failing, that we know that this member will fail at 50 pounds because of what it's made out of and all the stuff we have in our modeler. What's going to be the failure load for the truss? If this is a failing member, it's going to fail at 50 pounds. Yeah. Right. So it'd be a little bit less than 50. Right? A little bit greater or less? So if this is going to take 106% of the load and it's going to fail at 50, then it's going to get there before this gets to 50, right? So that's it. Then you have the failure load of the truss. Does everybody understand how that works? If not, you need to get with me today on it. Yeah. Can you speak up? Sorry. Not for the quiz, you're saying? It's theory. No, it's going to be on the quiz. I don't think that I would. I'm asking theory questions, so I don't think that's theory. That's more like computational. No, it's not going to be like, yeah, what did you divide the? Yeah, I'm not going to say, do you divide or multiply the load ratio times the failure load? No, I won't do that. But it is a quiz. The point of it is just for you guys to spend a little bit of time going, do I understand this stuff? So I don't want to be completely obvious of what's going to be on it. Okay, then the final thing is once we get the load that the truss fails at, how do we know its strength to weight? Yeah, divide the strength by the weight, and we get the weight because we know how long the members are, we know what they're made out of, we know their cross-sectional areas, their volumes. Yeah. That's a great question, but not in. So if you're doing the Snell version of the project, no, because we're only designing one conceptual truss, and then if we were actually gonna build it, then yeah, we would have two, and we would have cross bracing. There'd be a bunch of other stuff we were gonna do. But so this would be like the first step of designing a bridge. Would be design the shape of the truss, the materials, and then say, okay, now how are we gonna put the two together? We haven't covered that in this class, though. Professor Shapenko is doing that in his. His is using the exact same concepts as mine. It's just a different approach. You're actually you're saying you're starting with something that's not failing, right? And then you're saying, how do I make it cheaper? Okay, so strength to weight, and then and does everybody understand the difference between the empirical and the theoretical? This is not quiz stuff. But that's the other thing, is that then you're comparing the empirical to the theoretical strength and strength to weight, and then you're putting that in the context of your investigation. Okay, that was bombastic, but I think I covered all the stuff in the theory. It seems super straightforward to me, but if you have any questions about any of that, you should ask me. I didn't really spend any time on shear, but I think that's pretty straightforward. We said it's the same equation, and I feel like I'd spend enough time. Yeah, an hour and a half is plenty on that. Okay, so what I'm gonna do, so you can turn that light on, if you would. I know that you haven't been working on the projects right now in class, but I want to talk to each group briefly. So just start working, and then I'll get people to come up here maybe, or I'll go to each group individually.